Hey fellow nerds, today we will solve gate problems on OpAmp circuits from 2020 to 2024. This is our first problem. In the circuit given, the OpAmp is ideal. The circuit is supposed to show sustained oscillations. We have to find the values of R1 and the corresponding frequency of oscillation. Let us see how this can be done. For the OpAmp, input is given at the non-inverting terminal. So this much of the circuit can be considered as a non-inverting amplifier. Now, the output of the amplifier is given to an RC network, the output of which is given back into the input. So what we have over here can be considered as a feedback network. I'll mark VI here for the input signal, VO here for the output signal of the amplifier, and VF here for the feedback signal. It is kind of like this. Input is given to the amplifier output goes to a feedback network. Output of the feedback network is fed back into the original input. Let us say the gain of the amplifier is A and the gain of the feedback network is beta. Now, V output will be equal to V input multiplied by A. But the amplifier we have is a non-inverting amplifier. Its gain is 1 plus R1 divided by R. In the question, it is given that the circuit is supposed to give sustained oscillations. For sustained oscillations, we have to consider the Barkhausen criteria. The first criteria is that VF should be equal to VI. Now, VF is the output of our feedback network. The input is VO. Gain is beta. So, VF will be beta times VO. But VO is AVI. So, VF will be A beta VI. Now, if VF should be equal to VI, that means A beta should be equal to 1. That is our first condition. The second condition is that there should not be any phase shift between VI and VF. The phase shift does not have to be 0. Technically, it could be a multiple of 2 pi. Now, we know the expression for A, but we don't know what is beta. So, what we have to find out is an expression for beta, which is the gain of this much of the circuit. I have taken just the feedback network out. I'll mark the voltage over here at this point as V. Let us apply Kirchhoff's current law at this node. Current flowing through the capacitor in this direction can be taken as V minus V naught divided by the capacitive reactance of the capacitance 1 by j omega C. Or using S domain, where S is equal to j omega, I can write V minus V naught divided by 1 by SC. For this resistor over here, let us say the current is in this direction. It has a potential V at one end and 0 at the other end. So this current will be V minus 0 divided by R. Now there is one more current flowing through R and then through C to the ground. The series combination of R and C has a potential V over here and 0 over here. So this current will be V minus 0 divided by R plus 1 by SC. According to Kirchhoff's current law, the sum should be equal to 0. Now, rearranging this equation, we can write it this way. V multiplied by SC plus 1 by R plus 1 by R plus 1 by SC is equal to SC VO. Divide the entire equation with SC. That gives us V multiplied by 1 plus 1 by SCR plus 1 by SCR plus 1 is equal to VO. I'll add these two terms. I'll get SCR plus 1 divided by SCR. Let it be there. Let's take a look at VF. We have V at this point. V is divided between R and the capacitor. Out of that, whatever is dropped across the capacitor is taken as VF. So VF can be written in terms of V simply by using voltage division. VF will be V divided between R and 1 by SC multiplied by 1 by SC. Or we can write V by 1 plus SCR. That means V is VF multiplied by 1 plus SCR. Let us substitute V over here with Vf multiplied by 1 plus SCR. Then the equation becomes like this. Let us add these two terms. It will give us SCR plus 1 whole square plus SCR divided by SCR multiplied by SCR plus 1. But then 1 plus SCR over here and 1 plus SCR over here can be cancelled. Now, what we want is the gain of the network. It is final output Vf divided by the input Vo. From this equation, we can easily write Vf by Vo. It is SCR divided by SCR plus 1 whole square plus SCR, and this will be our beta. We have the beta in terms of S, but S is j omega. Let us replace S with j omega in this equation. That makes this term j omega Cr plus 1 whole square. Taking the square, I get j omega Cr whole square plus 2j omega Cr plus 1. Plus there is an SCR that becomes j omega Cr. If we square j omega Cr, j square becomes minus 1. So this term will become minus omega square C square R square. 2j omega Cr plus j omega Cr will become 3j omega Cr. We have a j in the numerator. Let us divide the numerator and the denominator with j. In the numerator, this j will get cancelled. For this term, if we divide it with j, it is like multiplying it with minus j. So the negative will be cancelled. We will get j omega square C square R square. If 3j omega Cr is divided with j, j and j simply gets cancelled and we get 3 omega Cr. If 1 is divided with j, 1 divided by j is minus j. So we get minus j here. Now the second criteria for sustained oscillations is that phase shift should not be there. That means in the denominator here we should not have any imaginary term. Here with j, we have omega square C square R square and minus 1. So for no phase shift, omega square C square R square minus 1 should be equal to 0. That means omega square should be equal to 1 by R square C square. Taking root on both sides, we can write omega should be equal to 1 by RC. If omega is 1 by RC, then frequency is 1 by 2 pi RC. This is the frequency of oscillation. So this term becomes 0. That means beta simply becomes omega Cr divided by 3 omega Cr, which is equal to 1 by 3. Now the first condition for sustained oscillations is that A beta should be equal to 1. If beta is 1 by 3, that means A should be equal to 3. A is the gain of our non-inverting amplifier. Gain of the non-inverting amplifier is 1 plus R1 by R. So 1 plus R1 by R should be equal to 3, or R1 by R should be equal to 2, or R1 should be equal to 2R. Option B is correct. Let us see the next problem. The op-amps in the circuit given are ideal, but they have saturation voltages of plus or minus 10 volt. Initial inductor current is 0 ampere. The input voltage Vi is a triangular signal with peak voltages plus or minus 2 volt and time period 8 microsecond. We have to find out which one of the following statements is true. The input is given over here. VO1 is the output we get over here and VO2 is what we get over here. Option A says VO1 is delayed by 2 microsecond relative to Vi and VO2 is a triangular waveform. Option B says VO1 is delayed relative to Vi and VO2 is a trapezoidal waveform. Option C says VO1 is not delayed relative to Vi and VO2 is a triangular waveform. Option D says VO1 is delayed by 1 microsecond relative to Vi and VO2 is trapezoidal. Let us figure this out. We can divide this circuit basically into two parts. The first part, which we have over here, is identifiable. It is a Schmidt trigger. Since the input is given at the non-inverting terminal, we can say it is a non-inverting Schmidt trigger. Now, what we have over here is an integrator. If instead of the inductor we had a capacitor, it would be a differentiator. Now, in the question, it is given that the input is a triangular waveform of peak voltage 2 volt and time period 8 microsecond. Let us plot it. Let's consider the Schmidt trigger part first. We need the upper threshold voltage and lower threshold voltage. The upper threshold voltage is given by R1 by R2 multiplied by the saturation voltage. Here R1 is 10 kilo ohm, R2 is 100 kilo ohm and the saturation voltage is 10 volt. That gives us 1 volt. Now the lower threshold voltage will be negative of R1 by R2 multiplied by Vsat, which is minus 1 volt. Now this means the output of the Schmidt trigger switches from minus Vsat to plus Vsat whenever the input crosses 1 volt, and it switches back from plus Vsat to minus Vsat when the input crosses minus 1 volt. Input crosses 1 volt at these points and it crosses minus 1 volt at these points. Let us assume that the output of the Schmidt trigger starts at the negative Vsat. Negative Vsat is minus 10. Now at 1 microsecond input crosses 1 volt, which means output of the Schmidt trigger will go to plus Vsat. Now the output will continue to be at plus Vsat unless the input crosses minus 1 volt, which is over here at 5 microsecond. Once input crosses minus 1 volt at 5 microsecond, the output of the Schmidt trigger will again switch from plus Vsat to minus Vsat. This will keep on happening. This gives us a square wave output. Also, you can see that the square output is 1 microsecond delayed when compared with the triangular input. Let us now find out VO2. VO2 is the output of an RL integrator. Output of an RL integrator is given by the expression minus R by L integral of the input voltage as a function of time dt. Here the input is the output of the Schmidt trigger, which is a square wave. It looks like this. Let us say initially VO2 is 0. In the first microsecond, this much is the area under the graph. Area under the graph will be 1 microsecond multiplied by minus 10. Let us use that in this equation so that we can find out the value of V out after 1 microsecond. So in 1 microsecond, V out will be negative R is 1 kilo ohm, L is 1 millihenry. So we get 10 to the power 3 divided by 10 to the power minus 3. Integral of V in dt is the area under the graph. We already saw it is minus 10 microvolt. Negative and negative gets cancelled. 10 to the power 3 divided by 10 to the power minus 3 is 10 to the power 6. But we also have a micro over here. So this becomes 10 volt. So every rectangle of this size, that is of 1 microsecond duration, will add plus 10 volt to the output if it is below the time axis, and it will add minus 10 volt if it is above the time axis. The negative is because we have a negative over here in the equation. So we start at 0. At 1 microsecond, the output will be plus 10 volt. What happens at 2 microsecond? This much will add another minus 10 volt. But we already have plus 10 volt. So the output will become 0. Now in the next 3 microseconds, minus 30 volts will be added. And the output will become minus 30 volt. Now in another 3 microseconds, plus 30 will be added and the output will go back to 0. Now this just goes on. In the next 1 microsecond, we'll get plus 10. And in the next 4 microseconds, we'll get minus 40. So the output will go back to minus 30. But there is one problem. For the integrator, the maximum output it can give is plus 10 volt or minus 10 volt. It cannot go up to minus 30 volt. So the output will be clipped off at minus 10 volt, like this. And that makes the shape of the graph trapezoidal. You don't really have to do this much analysis because all you have to find out is the shape of the graph. All you have to understand is that the output of an integrator when the input is a square wave is a triangle waveform. But if you calculate using this equation, you will see that the maximum value of the output will be greater than Vsat, which means the triangular waveform will be clipped off at the Vsat and we will get a trapezoidal waveform. So option D is correct. VO1 is delayed by 1 microsecond relative to Vi and VO2 is trapezoidal. Let us see the next problem. We have a circuit given. What we have to find out is Vout by Vin, which is the gain. Let us start by dividing the whole circuit into three parts. One with A1 in it, one with A2 in it, and the third one with A3 in it. Take a look at A1. Its input is given through a resistor R1 to the inverting terminal. We also have R2 as the feedback. So this much is basically just an inverting amplifier. Let us take its output and call it V1. Since A1 is an inverting amplifier, we can write the output V1 is equal to minus R2 by R1 multiplied by input. Let's take a look at A2 now. Its input is given at the non-inverting terminal. We have R1 and R2 over here. So A2 is basically a non-inverting amplifier. Let us call its output V2. Since A2 is a non-inverting amplifier, V2 will be 1 plus R2 by R1 multiplied by the input. Now V1 and V2 are given as input to the third stage, which basically is a summing amplifier. Both V1 and V2 are given to the negative terminal. That means this is an inverting summing amplifier. For V1, we have R4 and R3. For V2 also we have R4 and R3. So V1 will come at the output as minus R4 by R3 multiplied by V1. V2 will come at the output as minus R4 by R3 multiplied by V2. So the total output will be minus R4 by R3 multiplied by V1 plus V2. We have an expression for V1, we have an expression for V2. Let us use it here. Here we have 1 plus R2 by R1 multiplied by Vin. If we open the bracket, we get Vin plus R2 by R1 Vin. Then minus R2 by R1 Vin and plus R2 by R1 Vin will get cancelled. That gives us minus R4 by R3 Vin. What we need is the gain Vout by Vin. From here we can write Vout by Vin is minus R4 by R3. Option A is the correct answer. Let us see the next problem. We have a circuit with an ideal OpAmp. The baud plot of the magnitude in decibels of the gain transfer function is given. Omega is the angular frequency in radian per second. What we have to find out are the values of R and C. Let us see how this can be done. From the graph we can see that the maximum gain in decibels is 12. That means 20 log to the base 10 of the maximum value of the gain is 12. It actually is log of the magnitude of the gain, but over here what we have is a non-inverting amplifier. You can see the input is given at the non-inverting terminal. So the gain is going to be positive. That is why I did not put the magnitude part. Now from here we can write log of the maximum value of gain is 12 by 20, which is 0.6. So maximum gain is 10 to the power 0.6, which is approximately 4. Again, what we have is a non-inverting amplifier. Its gain is 1 plus R2 by R1. So that will be equal to 4. Here R2 is R, R1 is 1 kilo ohm. That gives us R is 3 kilo ohm. We also have to find the value of the capacitance. For that, let us again take a look at the graph. You can see that the gain is constant for some time, but at some point it starts decreasing. Why is that? It is because we have an RC circuit at the input. The RC circuit will provide a cutoff frequency, after which the gain will decrease. Now, what is cutoff frequency? Cutoff frequency, or the 3 dB frequency, is the frequency at which the gain in decibels becomes 3 decibels less than the maximum value. Here the maximum value is 12 decibels. 3 dB less than that is 9 decibels. When does the gain become 9 decibels? When log of omega becomes 3. So the cutoff frequency is whatever is the omega when log of omega is 3. Let us write this down. From the graph we see that at the 3 dB frequency, or the cutoff frequency, log of omega is 3, or log of the cutoff frequency is 3. So omega c will be 10 to the power 3, or 1000 radian per second. Now, what provides the cutoff frequency? The RC circuit we have over here. It is a simple RC circuit, so the cutoff frequency is 1 by RC. Let us call this resistor R3. Then we can write omega c is actually 1 by R3C. R3 is 1 kilo ohm. Omega c is 1000 radian per second. So C will be 10 to the power minus 6 farad, or C is 1 microfarad. Option A is the correct answer. Let us see the next problem. We have an ideal OpAmp circuit with a sinusoidal input. The 3 dB frequency is the frequency at which the magnitude of the voltage gain decreases by 3 decibels from the maximum value. We have to find out the correct options from the 4 given. The first option says the circuit is a low pass filter. Second one says it is a high pass filter. Third one says the 3 dB frequency is 1000 radian per second, and the fourth one says it is 1000 divided by 3 radian per second. Let's figure this out. You can see that the input is given to the inverting terminal. We have a 2 kilo ohm as the feedback and a capacitor in series with a 1 kilo ohm over here. If the capacitor were not there, we would say the gain is negative 2 kilo ohm divided by 1 kilo ohm. But we have a capacitor. Let us assume that whatever is the impedance we have over here is Z1, and whatever is the impedance we have over here is Z2. Then, since this is an inverting amplifier, the gain will be minus Z2 by Z1. Let us call the capacitor C, the resistor over here R1, and the resistor over here R2. Now, like we already said, the gain will be negative of Z2 divided by Z1. Here we only have a resistor, so Z2 is just R2. Here we have R1 in series with C. So the total impedance will be R1 plus the capacitive reactance, R1 plus 1 by j omega C. Let's give the values. C is 1 microfarad, R1 is 1 kilo ohm, and R2 is 2 kilo ohm. Let's cancel 10 to the power 3 from everywhere. That gives us negative of 2 divided by 1 minus j 10 to the power minus 3 omega inverse. We have to find out if the circuit is a low pass filter or a high pass filter. For a low pass filter, the gain will be high for low frequencies and it will be low for high frequencies. For a high pass filter, gain will be high for high frequencies, it will be low for low frequencies. So let us assume omega, or the frequency, is 0 and see what the gain is. Now, if omega is 0, omega inverse will become infinite. We have infinite value in the denominator, which means 2 divided by that will become 0. So at omega equal to 0, gain is 0. Now, to find the gain at high frequencies, let us take omega is infinite. If omega is infinite, omega inverse will become 0. Then this term will vanish. Gain will be minus 2. So obviously gain is 0 for low frequencies. It is minus 2 for high frequencies, which means what we have is a high pass filter. We also have to find out the 3 dB cutoff frequency. Cutoff frequency is provided by the RC circuit over here. So cutoff frequency will be 1 by R1C. Giving the values, we get it is 1000 radian per second. Options B and C are correct. Let us see the next problem. We have a circuit with an ideal OpAmp. A pulse Vin of 20 millisecond duration is applied at the input. The capacitors are initially uncharged. What we have to find out is the output voltage Vout at t equal to 0 plus. See, the question says the capacitors are initially uncharged. We know a capacitor cannot charge instantly through a resistor. And what we have to find out is the output at t equal to 0 plus. So at t equal to 0 plus, both capacitors will act as short circuits. At that moment, the circuit will look like this. Input is given at the inverting terminal. So what we have is an inverting amplifier. From the graph, we can see the value of input at t equal to 0 plus is 5 volt. Now the gain can be written as minus R2 by R1 because what we have is an inverting amplifier. Here R2 is 10 kilo ohm, but we do not have a resistor over here. But that is not a problem. We can take R1 to be 0, but that will make the gain infinite. So input is 5 volt, gain is infinite. Does that mean we get an infinite output? No, the value of Vsat is 12 volt. So the maximum output possible is 12 volt. Since what we have is an inverting amplifier, the output will be negative Vsat, which is minus 12 volt. The final answer is minus 12. Let us see the next problem. We have a circuit with an ideal OpAmp as shown in the figure. Magnitude of the input is very much less than the magnitude of VCC, and the magnitude of the reference voltage is also very much less than VCC. What we have to find out is the condition at which our output becomes 0. Let's figure this out. You can see that the positive terminal is grounded. That means here we have 0 volt. Since the OpAmp is ideal, whatever we have here is exactly what we have here. So here also we have 0 volt. That means at this point we get 0 volt. Let's take a look at R over here. It has a potential 0 at this end and Vin at this end. Let us take the direction of current through R to be like this. The value of the current will be Vin minus 0 divided by R. Now for R over here, we have 0 potential at this end and minus V reference over here. Let's take the direction of current to be like this. The current will be 0 minus V reference divided by R. Now for RF, at this point we have V out. At this point we have 0. Let us take the direction of current to be like this. Then that current will be V out minus 0 divided by RF. Let us now call this point A and apply Kirchhoff's current law there. Vin minus 0 by R is coming into the node. V out minus 0 by RF is also coming into the node. 0 minus VRF divided by R is going out of the node. So we can write it like this. Vin by R minus Vref by R plus V out by RF is equal to 0. Or we can write V out by RF is 1 by R times Vref minus Vin. Now what we have to find out is the condition at which V out becomes 0. If V out is 0, then the left hand side of this equation is 0. Then the right hand side should also become 0, which means V reference minus V in will be equal to 0. So when V out is 0, V reference minus V in is 0, which means V in should be equal to V reference. Option A is correct. Let us see the next problem. We have a circuit with an ideal OpAmp. V reference is fixed. When V input is 0.1 volt, V output is 1 volt. And when V input is 1 volt, V output is 6 volt. What we have to find out is the value of RF by Rin. It is also given that Vout is measured across RL that is connected at the output of the OpAmp, which is basic information. Let us figure this out. We'll start by marking the potential at this point as V. Now assume that through Rin a current flows in this direction. The current will be equal to Vin minus V divided by Rin. Let us also take the current through Rf to be in this direction. Then that current will be Vout minus V divided by Rf. No current will flow into the OpAmp because our OpAmp is ideal. Let us apply Kirchhoff's current law at this node. Sum of the two currents should be equal to 0. Vin minus V by Rin plus Vout minus V by Rf is equal to 0. Or we can write V multiplied by 1 by Rin plus 1 by Rf is equal to Vin by Rin plus Vout by Rf. Let's add these two. We'll get Rf plus Rin divided by Rin Rf. If we add these two, we get Vin Rf plus Vout Rin divided by Rin Rf. Rin Rf can be cancelled from both sides of the equation. To get an expression for V, let us take Rin plus Rf to the other side of the equation and we get V is Vin Rf plus Vout Rin divided by Rin plus Rf. Now take a look at what is happening over here. We apply V reference. V reference will be divided between R1 and R2. Out of that, whatever is dropped across R2 is what is given to the positive terminal. So the voltage we get at the positive terminal can be found using voltage division. It is V reference divided by R1 plus R2 multiplied by R2. But what we have is an ideal OpAmp. So whatever we get here is exactly what we get here. This will also be equal to V minus. Again, what we have here is our V. So this is also equal to V. Therefore, we can equate this one to this one. Vin Rf plus Vout Rin divided by Rin plus Rf is equal to V reference R2 divided by R1 plus R2. Now, in the question it is given that Vout is 1 volt when Vin is 0.1. Vout is 6 volt when Vin is 1 volt. Let us substitute these two sets of values in this equation. For Vin being 0.1, I'll give Vout 1 volt. That gives me this equation. Instead of Vin, I have written 0.1. Instead of Vout, I have 1. Let's call this the equation number 1. Now, let's give Vout 6 volt and Vin 1 volt. Let's call this equation number 2. You can see that the right hand sides of both these equations are the same. That means the left hand sides should also be equal. Rin plus Rf can be cancelled from both sides. We get 0.1 Rf plus Rin is Rf plus 6 Rin. Taking both Rin terms on one side and the Rf terms on the other side, we get minus 0.9 Rf is 5 Rin. So Rf by Rin becomes minus 5 by 0.9, which is negative 5.55. But all of the options given are positive, which they should be, because what we are finding is the ratio of resistances. It cannot be negative. So we have to say none of the options are correct. The problem must have been with the values we got over here. Maybe these are not the output voltages we get for these inputs. Let us see the next problem. The components in the circuit given are all ideal. R is 2 kilo ohm, C is 1 microfarad. What we have to find out is the 3 dB cutoff frequency of the circuit. This is the circuit we have. Now, I would say this is a very simple problem, but made to look like a complex one. I'll explain to you why. You can see that the positive terminal is grounded, which means here we have zero potential. Since the OpAmp is ideal, whatever we get here also. So at this point also we have zero potential. That means over here we have zero potential and over here we have zero potential. Take a look at 2R. On both its terminals it has zero potential, which means no current is flowing through it. It is doing nothing in the circuit. How about 2C? It also has zero potential on both ends. It is also not doing anything in the circuit. So let us just remove them. Since no current flows through 2C and 2R and they don't do anything in the circuit, let us remove them and make the circuit simpler. Now, the question is to find the 3 dB cutoff frequency. Who is providing the cutoff frequency? The RC circuit we have over here. So the 3 dB cutoff frequency will be 1 by 2 pi RC. Values of R and C are given. R is 2 kilo ohm, C is 1 microfarad. If we give the values, we get the 3 dB frequency is 79.58 Hz. Option D is correct. Let us see the final problem. Let us see the next problem. In the circuit given, all the components are ideal. Vi is 2 volt. We have to find out the current IO if the input is plus 2 volt. IO is the current that is flowing over here. Let us figure this out. It is given that the input is plus 2 volt. Since the OpAmp is ideal, here also we get 2 volt. Let us mark it over here. Again, the input is given at the positive terminal, which means what we have over here is a non-inverting amplifier. Its gain will be 1 plus R2 divided by R1. R2 and R1 are both 1 kilo ohm. So we can write V output is 1 plus 1 by 1 times the V input. But V input is 2 volt. So V output becomes 4 volt. So the potential we get over here is 4 volt. For the 1 kilo ohm resistor, it has 4 volt here, 0 volt here. So a current will flow in this direction and it will be equal to 4 by 1 kilo or 4 milliampere. For this 1 kilo ohm, it has 4 volt here and 2 volt here. So a current will flow in this direction and it will be equal to 4 minus 2 divided by 1 kilo or 2 milliampere. Let us apply Kirchhoff's current law at this node, which is the output node. 2 milliampere is going out of the node. 4 milliampere is also going out of the node. I naught is coming into the node. So I naught should be equal to 4 plus 2, which is 6 milliampere. The correct answer is 6. So that's all about it for today. See you in the next video. And please don't forget to subscribe.